In this video, we are going to look at Taylor dispersion and how exactly the entire thing works. And we're also going to look at an example where we take the Taylor dispersion formula and we solve it using the similarity solution. So what is Taylor dispersion? This was explained by G.I. Taylor in his very famous paper in 1953, where he describes how a soluble substance which is injected rapidly into a fluid that's flowing in a tube, what the kind of trajectory looks like, where the peak solute concentrations are created, whether it's just convection or whether there's diffusion as well. So this is the original paper proposed by Sir Geoffrey, which is called Dispersion of Soluble Matter in Solvent Flowing Slowly Through a Tube. A very famous paper where he says that if a conducting solution like brine is injected into a tube through which water is flowing, the region in which it is concentrated moves downstream, as expected. And then he quotes a similar method used by Griffiths in 1911, where Sir Griffiths had also done experiments designed to measure the viscosity of water at very low speeds of flow. And then he goes on to describe what exactly the droplet was and the experiment that Griffiths had conducted. And then he quotes something from Griffiths' paper in 1911, where he says that the full mathematical treatment is not attempted, but he's trying to give an elementary consideration which is incomplete, and how that's advantageous in dealing with the given experiments. And he says it can easily be shown that if the intensity of color were constant over a cross-section of the tube, the color would diffuse along the tube exactly as if it were water traveling in a solid column, which is true. So basically what he's trying to say is that if that were the case, we wouldn't see these arrows which depict the diffusion. It will just be something which just flows like this along the tube. But that's not what we see, right? We do see the entire width of the tube also getting colored. He says the intensity of the color cannot be absolutely constant over a cross-section, except in the theoretical case of a capillary tube of infinitely small bore. But the experiments show that when the rate of flow is small, the error involved in this assumption is not great. And then he goes on to explain the rest of it by stopping the supply, what happens, and how the changing the speed of flow also makes a difference. Now what's interesting is G.I. Taylor then says that the only parts of Griffith's statement that do not seem clear are those which follow the words "it can be easily shown that" and "it is obvious that." So he's saying that to him, and even to us, it's not obvious that the flow regime which he described is actually the case, and if it is, then why is it the case? And the statement describes two experimental results which seem almost remarkable, though their discoverer does not comment on them in this sense. So he's providing a bit of criticism about Griffith's work, and then the rest of the paper, he goes on to give a full mathematical treatment about it and show the entire Taylor dispersion phenomena occurring. So with that background, we'll try to solve a question using the similarity method. So as described, if a soluble substance is injected rapidly into a fluid flowing in a tube, a sharp peak in the solute concentration is created, which is this. As the peak travels along the tube, it gradually broadens, which are these arrows. Right? It's not just, as we said, the peak moving along. That's not what happens. And this resembles molecular diffusion, but this is actually a combination of diffusion as well as convection. Sort of like this. So the diffusion causes it to move along the width, which is what is happening here. And in this case, and this is the convection which moves it along the tube. So actually this also involves some amount of convection, and this also involves some amount of diffusion. So it's a very complex combination of both. This is a formula that Taylor suggested, which says that it relates the variation of the mean concentration with time compared to the mean concentration variation with the width in this case, with the length in this case, which is a z. And it's the proportionality constant is the dispersivity, which is k. And this is how we get the average solute concentration for a cross-sectional area, as we know. And then he introduces dimensionless variables, as we do in any transport phenomena question. where he takes theta to be this relation between z and r, which is along the width, the length, sorry, and he takes a tau variable for the time, which involves the d factor, and that k by d gives us the dimensionless diffusivity. And with that, we have this relation, which he then goes on to further expand with the moment variables, etc. But this is the bare metal equation which we're going to use. So with this, let's take an example. This example is from Professor Dean's book, edition 1. This is question number 9, the 11th question of chapter number 9, where they take the Taylor phenomena setup and they say that you can apply this even for step pulses. For step input, you don't just have to do this for, say, pulses that are getting injected into a tube. You can even do this for step cases, which is what this question is asking us to do. So suppose you have a step change in a solute. It starts at some C0, where this entire part is z less than 0. And then at z equal to 0, the step change is applied and the concentration becomes 0. So this is for z greater than 0. So they've asked us, one, with using the similarity method, we have to find the average concentration. And there's a little hint given. And after that, we also have to use that solution to find what is the length over which 95% of the concentration change will occur at some time t. So here I've already solved the question because it's a bit long. It starts with this schematic of how the step looks. So first we have the concentration step at C0, which is for z less than 0, and then at C0, z equal to 0, we can see that the step goes on and the concentration becomes 0. So for A part, we start with the Taylor dispersion equation, as we saw earlier. And then we have our initial conditions and the boundary conditions. So the initial conditions is at t equal to 0, what was the situation, which is given in the question. At t equal to 0, c is equal to c0 for z less than 0 and c is equal to 0 for z greater than 0, and that's exactly what we've reproduced here. Then there's the boundary conditions, which is important. As in any transport question, we need the boundary conditions to solve our governing equations. So one of the boundary conditions is that at z equal to minus infinity, which is somewhere far away along the length of the tube for some time t, the concentration will be C0. Why? Because we say that the step input before z equal to 0 is at C0, so that will extend all the way till minus infinity. And similarly, the step input which is being given for z greater than 0 is 0. So that means even at plus infinity, it's going to be 0, which is in this direction far off right at the end. These form our boundary conditions. Now we non-dimensionalize it. So we have our dimensionless quantities. I've taken theta to be the average concentration upon the initial C0. And then I have my similarity variable here, which is eta, which is I've taken as z upon 2 root of kt, which is a standard form. Now if I write the boundary conditions in terms of these quantities, we can see that theta is now only dependent on the similarity variable, which is eta. So when z tends to infinity, eta also tends to infinity. When z tends to minus infinity, eta also tends to minus infinity. So that gives us the updated boundary conditions of theta at infinity equal to 0 and theta at minus infinity equal to 1. Now we start solving the similarity solution. As we know, the similarity solution takes the form of the error function, which is this 2 by root pi of 0 to eta e raised to minus s squared ds. Right? Standard form. So our theta ends up being, because it's a step function, it's just linear. So it ends up being some a times of the error function plus the constant of integration, which is b in this case. Now we have to find a and b. I've written here, yes, that we know the error function is, and that's what this is. So now we don't know what a and b are. We don't have enough equations yet. Or do we? We know that the error function is an odd function. How? I've shown that calculation here. If we invert the integral, then it doesn't make a difference because e raised to minus s square is an even function. So it's still going to give the same results on the inside. But then when we now invert the integral by taking this up, it will become negative because that's a normal inversion of an integral. But now notice that this is basically this part, if we exclude the minus sign, this is basically the error function of minus eta. So that gives minus of the error function of minus eta. So if fx is equal to minus of f minus x, that means f is an odd function. So this tells us that the error function is an odd function. Now this is useful to us. Why? Because our boundary conditions are of the plus minus x format, plus infinity and minus infinity. So this way, now we have two equations. So we're able to solve two equations, two unknowns. These are our two equations. Now if I add 1 and 2, notice that here these two are negatives of each other. So if I add these, this gets cut. So that gives us b is equal to half. And now we substitute back into either of the two. I've put it into 1. We know that the error function of minus infinity is minus 1. How? If you put minus infinity here, that's what we'll get when that's the standard form. So using this, we can get that a is equal to minus half. So finally, this is our theta. And from this, we have gotten our average concentration as this. I ran out of space. 2 root kt. And that's what we were asked to find. So that completes part A. Now for part B, we were asked, I'll just go back. We were asked to find what the length should be over which 95% of the concentration change will occur at some given time t. Here length is basically our z. So we have to find what z should be given 95% of the length of concentration has changed. This basically means our error function is equal to 95%, which is 0.95. Now there are standard tables for the error functions. For various values of eta, we know what the value of the error function is. So from that standard table, we find that for an error function value of 0.95, our eta comes out to be 1.4. This is from the standard table directly. And we know what our eta formula is. It's this z upon 2 root of kt. So we just equate that. And this is basically going to be what our LT is. This is the final answer. Dependent on t, because they've asked us for LT. They've not given up a specific time, which is why it's a function of t. K is a constant. So our length for which the 95% concentration change occurs is 2.8 times root of kt. And that's our final answer. So with this, we looked at what Taylor dispersion is. We looked at Professor G.I. Taylor's work, Dr. G.I. Taylor's work, and his comparison of and criticism on Dr. Griffith's work. And we also solved a question using the similarity method of the Taylor dispersion system.